Tonight, we have the privilege to have Father Chris Corbally present the Vatican Observatory in Arizona. Father Corbally is a Jesuit priest on the research staff of the Vatican Observatory and an adjunct professor at the University of Arizona. He was vice director for the Vatican Observatory Research Group in Tucson until 2012. Father Corbally was born in London. Can I tell him the year you were born?
Oh, if you like, yep.
1946.
There'll be a number of us born at the same year, I bet.
He earned his BS in physics at the University of Bristol, England in 1971, his master's in astronomy at the University of Sussex in Brighton, England in 72. He was ordained a priest in 1976, and he obtained his PhD in astronomy at the University of Toronto in Canada in 1983. He's a member of the Royal Society, the American Astronomical Society, the International Astronomical Union. By the way, how did you vote on Pluto? Wasn't that the IAU?
I put the vote to the Assembly as a chairperson of the Resolutions Committee, but I didn't vote because someone stole my voting card.
Oh.
Don't blame me.
Yes, I think so. Good answer. Good answer. I still think of Pluto as a planet, so I don't consider that a valid.
It's a planet. It's a dwarf planet.
Well, yes, yes, absolutely. Anyway, so let's see. Where am I at here? He's also a member of the Society of Astronomical Sciences and others. That's where I met Chris, was through the SAS. His research interests include multiple star systems, stellar spectral easy for me to say, stellar spectral classification, peculiar galaxies, galactic structure, star formation regions, telescope technology, and many other areas. Although he has many peer-reviewed publications and has published at least 4 books. And one of them is the stellar spectral classification, which he co-authored. This is one of the books that the spectroscopic discussion group uses and considers to be our Bible for stellar spectra. So good work there. So the Vatican Advanced Technology Telescope is a Gregorian telescope used for observing in both the optical and infrared regions. It's a 1.83 meter telescope in diameter. The telescope achieved first light in 1993, and it's situated on Mount Graham in southeastern Arizona. I met Chris, like I said, through the spectroscopic discussion group, and he has graciously agreed to present to us tonight. What I'm looking forward to a lot is the Vatican Observatory in Arizona, of course. So now, with my sincerest thanks for accepting the invitation. Good evening, Chris. Welcome. And now please take us through the history of the Vatican's observatory and explain how it became a part of the Arizona landscape. So, Chris, go ahead.
Good. Thank you so much. Let me, wonderful to be here. Thank you indeed. Now, if I share this screen, can you see the screen?
Yes.
That's wonderful. Okay. Okay. So we've got 3 words up there in the top left: Vatican Observatory in Arizona. And it's always a bit of a puzzle how these all 3 go together. So I'm going to try and explain that to you, as well as give you an idea of what we're all doing here. Let's just get it all going.
Go ahead.
There we go. Good. This is a picture, not of great artistry, but it's in our, kindly painted and given to our Vatican Observatory. It's in our headquarters out near Rome. And it does show in the faces of these people are history. Gregory the 13th, 1582, Angelo Secchi, director of the Vatican Observatory in the mid-19th century, Leo the 13th, 1891, Pius XI. So let's see how these all fit in. And there's another date as well around 1980 that is good to remember in this. If my voice drops, please let me know. Okay, you promise?
Promise.
Okay, lovely. So let's start then in the Vatican. Looking down on it, St. Peter's there right in the middle. You've got the Vatican Museum all going along there to the Sistine Chapel. And if we do this little thing, the circle or the ellipse there is over the Tower of the Winds. So this is what it looks like, Specula Astronomica Vaticana, because yes, it was part of our observatory at the starting years of the observatory, and also, right back at the beginning, because the Gregorian calendar reform in 1582. So it was at that time that it was realized that the calendar was getting out of step with the seasons. And this is particularly important for the church when Easter in the Northern Hemisphere was moving back into winter. And yet Easter is a celebration of new life, the new life of the risen Christ. So what to do about it? Well, let's reform it. And so the Tower of the Winds, while maybe used for some of the observations to help, was probably mainly used to demonstrate to Pope Gregory the 13th, remember that figure, that the calendar was indeed out of date. This is inside the Tower of the Winds, and on the four walls of this room are painted the four winds. Also, at the right time, the sun will come through this little hole and go right in the center of this circle at the equinoxes. Now, in Gregory's time, Pope Gregory's time, this was not happening at the equinox, so something needed to be done. Now, this kind of thing is very much illustrated in other churches. You'll find these ways to see the calendar as well at noontime. So, reform of the calendar, promulgated in 1582. There was a Jesuit, I'm a Jesuit, by the way, a Jesuit mathematician, Christopher Clavius, who was on the team doing this. So beginnings then of the Vatican's involvement in astronomy for a very practical reason, the reform of the calendar. Observatories have, national observatories have arisen because of other very practical reasons, like navigation or timekeeping very often as well. So like the Naval Observatory near DC. Let's jump then through various manifestations of the Vatican Observatory. So actually Jesuits at the Roman College being interested in astronomy, having an observatory for a little while, and then kind of the thing lapses as the enthusiasm goes. But in the middle of the 19th century, 1850, Father Angelo Secchi was appointed director of the Vatican Observatory. He had all kinds of skills, meteorology being one of them. The first weather maps for Italy were done by Angelo Secchi, using the new technique of the telegraph to get him the information of what was happening in various parts. But above it, you can see hand-drawn spectra. In those days, the photographs were not sensitive enough to make spectra. So this had to be, all these lines, these features had to be hand-drawn. And he had something like 4,000 of these. And it was clear that they weren't all the same. They fitted into classes. And here you can see the classes, his type 1 up the, whatever it is, no, type 2 up at the top, which is like our sun there with its G band. Type 1 here is strong hydrogen lines. So like Sirius is the star. Alpha Orionis is type 3 with the lovely bands of titanium oxide coming out here. Oh, that, and then type 4, or at least the bottom one, kind of 3 plus, is a carbon star. We'll come back to that in a little while. Oh, I'm sorry. No, it's another M-type titanium oxide bands. But he also distinguished a 4th type, which was the carbon stars. Okay, where did he do all this? In a telescope on top of the Church of St. Ignatius in Rome, which was designed, the pillars were strong and designed to have a dome on top of it, but the dome was never built, so it was ideal for Father Angelo Secchi's observatory. He died, excuse me, I've got what I call traveler's cough, having traveled around. So just recently came back last Friday. And so he died in 1878. And meanwhile, a couple of years before that, Rome had been overrun by the Italians, and actually any equipment of the Vatican taken over by the Italians. But Angelo Secchi had such a reputation, they did not take his observatory until after he died. So after he died, the Vatican didn't have an observatory. What to do? Well, wait just a few years. Pope Leo XIII did the refounding and restructuring of the Vatican Observatory. And in 14th of March, 1891, he had this sort of letter describing why he did it. The core of it was that everyone might see clearly that the Church and her pastors are not opposed to true and solid science, whether human or divine, but they embrace it, encourage it, and promote it with the fullest possible devotion. So this was the refounding of the Vatican Observatory in Vatican City. So if you remember that picture of Vatican City, there's actually a wall on the hill in the back there, and on that the various telescopes were founded of the Vatican City. Now, city. Something happens in city as things develop and lights get turned on and we get light pollution. So it was actually light pollution that made observing no longer efficient in the Vatican City. And at the time that was happening, a concordance was signed between the Vatican and the Italian government, such that it was now possible for the Vatican to have property outside Rome. So there was a move indeed of the Vatican Observatory out to Castel Gandolfo, about 15 miles outside of Rome at an elevation of about 1,000 feet. And these 2 domes that were then put in the 1930s were a gift of the Catholics of Germany. So we have 2 telescopes there. I'm sorry, really 3, because this one here is a double telescope with both a refractor and a reflector on the same mount. And this one is one designed for visual in the middle. So these will work fine in the lovely atmosphere of Castel Gandolfo for a while. But again, lights caught up as people lived out there, light pollution. And in 1980, we established a relationship with the University of Arizona. So it's from Tucson, Arizona, I'm speaking now. And we had affiliation with the university. So Mount Graham. Mount Graham, ooh, that comes later. It comes in 1993, because in the introduction it was dedicated. Actually, in 1993, it just had the primary mirror there. The secondary had not yet put in place. So we literally had first light just before dedication. So what's the story then of the Vatican Advanced Technology Telescope, conveniently called VATT, and that construction name has remained with it, though it's due to the very generous gifts of some people after whom the telescope is named the Alice P. Lennon Telescope, and the building the Thomas J. Bannon Astrophysics Facility. And this person, Tom Bannon, who used to construct all kinds of things, said, this is the first time I've had an astrophysics facility named after me. So Tom was pleased. What was that all about? How do we come? Well, because initially in Tucson, there are a lot of telescopes of the university, wonderful ones, of which I've used some on the Kitt Peak very much. But right at the time we became affiliated with the university was the project to make enormous telescopes, the kind of the new generation of telescopes we're having now, and how to make the mirrors, if they were solid mirrors. The answer was in this way, honeycombed to make them light, and you can see the honeycombs there, and very steeply curved, so that the focus was very short indeed. You didn't have to make a huge building. And so this mirror was made as a prototype in a rotating oven. You can see the bands there. There was one of the engineers who was able to run and jump on this rotating platform 15 times a minute. You can imagine it going around, and still manage to function. So he was a very valuable part. The oven was on top, and this is looking, with a camera inside the oven at the molten glass going down inside, kind of going through the cracks of the forms that you can see them here, of ceramic forms that gave the structure of the honeycomb. So that process is another story and a fascinating one. Yes, it was successful. Richard Wortley poses with the completed mirror. So there's the actual thing. The mirror is, as described, 6 foot in diameter, 1.8 meters, and like a rather, large salad bowl. So where to put it? Well, right at the time, obviously the plan was to grow up in size of these mirrors to eventually the 8.4 diameter mirrors, which are currently being made. And the place for the binocular telescope, the large binocular telescope with 2 of these 8.4 meter mirrors, was chosen to be about 75 miles to the northeast of Tucson, up on Mount Graham. Though that's as the crow flies. As you go round by road, it's twice that, with the last 30 miles being a mountain road. Why Mount Graham? It was high, 10,500 feet where the telescopes were going to be, and it was relatively far away from Tucson for the light pollution, and just a good climate. What you can do, of course, is the thumb test. This is a picture taken on the University of Arizona campus with this lamppost, the head of it concealing the sun. Do the same thumb test on the top of Mount Graham with the aid of the top branches of a tree, and that's what you see. Just about no scattering right up to the sun, and that's the quality of the atmosphere up there and why we're built there. So, okay, construction happened. It's a long story. Cut it short. This is putting the mount in place with the ring where the telescope mirror and its holder will go, and then obviously the optical support system above it. You'll see the whole thing is terribly squat. It's crazy. The focal ratio of the mirror is 1.0. No one in their right mind designs a telescope like that. But we did, because there had to be that shorter focal ratio in order to make the large 8.4-meter mirrors work, and two of them together in the large binocular telescope. So we had this mirror, which we called, at least the engineers called, the LBT-0, Little Big Telescope, because it was smaller than the large binocular telescope that was being planned, but it had many of the headaches because of the mirror. But obviously, an effect of having such a compact system is that you have very little dome seeing. You don't have a huge cathedral-like dome to put it in, and everything is compact and right on top of a mountain. So it all worked very well. And eventually then, yes, it came together, and we had the dedication. This is the winter 93 to 94 as things were getting established inside it. The secondary mirror, as I say, came in the summer of 94, and then observations started in the beginning of 95. So that's the kind of the history of it. So we're celebrating now, I suppose, 31 years since its dedication. Now, stabilizing and upgrading a telescope. I was, from our Vatican Observatory point of view, in charge of the telescope and on the team that was designing and building the telescope. Now, the mount was made by a firm in Los Angeles and was duly shipped along, actually went into a hangar at a nearby airport to Tucson on the west side. And when it was in the hangar, got things working, and then various modifications were being made. And I asked our chief engineer, Bob Nagel, who was actually chief engineer for Stewart Observatory and had experience of building telescopes. I said, Bob, did we not specify correctly the telescope for L&F engineering to make it? Why are we doing all this work on it now? And Bob, being a good engineer and experienced, said, Chris, relax. A telescope is a living thing. If you stop working on it, it dies. And so in the course of the last 31 years of the telescope's lifetime, steady work has indeed been done on the telescope to keep it alive and performing even better. So what you're looking at here is, you can recognize the optical support system there, looking down on the mirror, and it's F1, so it looks crazy, and then fixing something there. They're putting angle brackets there. Michael France, who's actually still with us as engineer, with the guide camera assembly underneath the telescope in the sort of guide box area things. So, yeah, improvements. Certainly there had improvements in around year 2000. We got a grant from the Kresge company to upgrade the VATT. And then again, improvements just in the last dozen or so years. M2 is the secondary mirror at the top. Positioning it is a real business. We had a kind of a self-designed, positioner made at Stewart Observatory, which worked remarkably well for a good number of years. But after this kind of time, 20 years or so, improvements have been made. Hexapods had come down massively in size, and so we could get even better control of positioning the mirror. To give you an idea, the focus needs to be positioned, so that's the secondary mirror and the primary mirror need to be positioned within 2 microns to keep the imaging. So what's 2 microns? Get hold of a piece of your hair, chop it down, cut across, and then chop that 25 times into equal parts, and a 25th of a hair is about 2 microns. it's not much when you're given these things. So all kinds of other things, the computers, HP servers, instrument interface, guide cameras, those are actually changed again, safety systems, all kinds of things. Oh, M1, that's the primary mirror reilluminization. The conditions up there are pretty good, but it does need reilluminized every now and then. Each summer, the mirror, the primary mirror is, hand washed very carefully and takes with skill. But every now and then we need to reilluminize the mirror. So take it back to Tucson, reilluminize it, and then bring it back to the mountain. Sounds simple, doesn't it? Except when you see that the only way to get the mirror is out through the dome slit and all the way down to the ground on a truck, and then down a bumpy road to Tucson, and then put it back again when that's finished. And finally, make sure that it's not done in too much sunlight. Goodness, look at all the sunlight there, because you don't want the mirror to be unduly warmed on one side or another. We seem to have got away with it that time. Okay. So, we've got our telescope, we keep improving it. Now what do we do? The whole point is the science, isn't it? So a couple of just sort of projects which it's been doing, as well as a bunch of others, and you can ask me about that as well. But one is called the Eden project. And that's looking for planets around other stars that are likely to be suitable for life. So it's really a search for Eden or life around other planets. You can see a whole bunch of telescopes are involved in that project, including the VATT there. Other ones, the pictures of them that here in various parts of the world to do the monitoring of the eclipses. So yes, that's rather fun. That's night on Mount Graham. The only problem is you'll not see that. It's 10,500 feet, and the lack of oxygen makes your eye, very inefficient. But if you have a camera, then that's what it can see. And if there's a little light put on at the sub-millimeter telescope, which is our neighbor, a 10-meter sub-millimeter telescope, you'll be able to see that and a faint glow in the background of the large binocular telescope with its two huge mirrors there. And it looks like we might get a little, oh, that's a bit of Safford in the background. Okay, that's fine. And what we're looking at, of course, is the light curve, follow-up light curves of planets, at least occultation, that have been, transits that have been discovered by the TESS telescope up in space. And so that's what this network is designed to do. Again, it needs a team and a skilled team, and it's great to be able to contribute to that. It's not my project. The one who's mainly involved from our point of view is our current vice director of the Vatican Observatory, Paul Gabor, but I know Rich Boyle has also helped with that as well. And just recently, at least a year ago in May, a temperate Earth-sized planet with tidal heating transiting an M6 star and an artist's concept of the volcanoes all over it. I don't think I'd like to live there, but you never know. I'd say we go for M stars, for this kind of thing because it's the easiest. I still think, the Earth does pretty well with its G25 star. For a long time, I waited to get a spectrograph on the telescope because spectroscopy, in the tradition of Angelo Secchi, is what I do and love doing. And at last, I used a spectrograph at the University of Arizona telescope on Kitt Peak, on the 90-inch, extensively for various things and wonderfully. But there's nothing like having a spectrograph on your own telescope. And so in 2011, the spectrograph was put on. The optics are refracting optics, so that's why it's rather large. And it has resolutions, the lowest resolution is about R equal 1,000, and then there's 2,000, and the highest about 4,000. So it works very well for what I do, which is classification, and for other things as well. It's also been used to characterize and find quasars, so it can do a good number of jobs. A project with the VATT, or at least the VATT helped. Spectra, what spectra can do is see where a star fits in the general stage of evolution and among its other stars. And this is best seen in something called the Hertzsprung-Russell diagram, discovered, as it were, by two people. On the bottom, you can see spectral class, and then there's luminosity up here. Temperature on the top, of course, being astronomers, low temperature is on the right-hand side and the high temperature is on the left-hand side. Just as our spectra that we use tend to have red on the right and blue on the left, but that's astronomy. It's always backwards, and just as absolute magnitude goes backwards, it gets more negative as the star gets brighter. So here we have the bright, very hot stars and the faint, very cool stars. Most stars are lying down here on the main sequence with the sun around G2 there. Giants, supergiants, as these stars go through other stages in their lifetime and ending up as white dwarfs. So we can characterize them like that. Now, for a real spectrum, a case study of a peculiar star, TU Taurus. And Joe knows all about this one, because it's also a project of the spectroscopy discussion group. Richard Gray, who is a grad student at the same time as I was in Toronto, found in a spectrum taken with the Lamos telescope, a Chinese wide-angle telescope taking around 4,000 spectrum at the same time. He found in a spectrum taken in 2013 that this star, TU Taurus, as expected, had a huge amount of output in the red because it's a carbon star, which are very red, very dusty, and very red. But also, the spectrum showed in the blue its companion star. Now, it was known to have a companion since the 1940s, but didn't know really what kind of star it was. This spectrum showed both that it was a very blue star, an A-type star, and if we look a little further, that it was highly odd. This is the middle spectrum. I hope you're used to wiggles for stars. So here we have intensity, and it's rectified so the continuum of the star, so the output of the star is all put on a straight line. And at the bottom, we have wavelength with red on the right and blue on the left. And these, what we're looking at then, are absorption lines. The big teeth are the absorption, excuse me, of hydrogen, and that dominates in A-type stars. There's other features, the narrowness of these, or the width of these hydrogen lines tells you that it's not a main sequence star, dwarf star like our own sun, but it's evolved a bit. It started to change its source of energy, and it's actually a giant star, or just a little bit not quite so bright as a giant star, 3 to 4 star. And this is the standard. Well, this is the Lamos spectrum taken in 2013. And you can see all kinds of other features. And this is one taken with the VATT in 22, so a couple of years ago, where some of these features are present, but others are missing again to the extent this star, this companion star, changes. A close study of the spectrum of the A-star companion revealed an unusual chemical composition with enhanced abundances of nuclear S process elements. These are the slow neutron capture process that takes place in a star that's reaching the end of its lifetime. And when there are kind of flashes, explosions in shell of, in this case, of helium shell that's in the outer part of the star. And so the slow neutrons, slow process of capture, making these rather unique S process elements such as strontium and barium. Here we have barium, really nice and strong. And next to the calcium there, we have strontium, way stronger than the standard star. And there'll be another strontium down here. So very odd, but it varies. You don't always see these S process elements, but you are seeing An 24233, which is indicative of a shell. So there's a shell around this A-type star. What's suggesting us that the A-type star is being contaminated with these elements, these S process elements, by mass transfer from the carbon star. Okay, needs to be looked at further, was Richard's thing, and especially when I took a spectrum as well. Because when you, let's just pop back, take this hydrogen line, and this is the spectrum taken with that at the bottom, and you see it's maybe not totally symmetrical. And this in continuous line shows the spectrum taken with VATT, and the dotted line is a standard star. Take the difference between the two, and you get this big jump up and then down in intensity, which, thanks to the Doppler effect, is showing you that material is falling onto the A-type star. So it's accreting this carbon star material, which is rich in the S process elements. Ooh. But that's not the end of the story. Thanks to the wonderful group of what I call small telescope scientists. Other people call them amateurs, but I feel they're much more than that because they're doing wonderful science. And they have been observing much more regularly than Richard can do, Richard Gray can do, my colleague, and I can do. I go to VATT 3 times a year, so I can't do regular things, but every night that's clear, a wonderful team of small telescope scientists can observe. And what happened, discovered that the A companion was fading. So you can see the, as it were, the hydrogen teeth there clearly in the top, but it's been fading and then maybe come back a bit and then kind of faded and gone. Disappeared completely April last year. What's happened? And the A-type star remained hidden from view for over a year. In April this year, 2 of our group managed to find that very faintly here and here you can see hydrogen. It's a rather fainter spectrum, so apologies. So April, yeah, there were signs of the A-type star again, but it's disappeared again. Just a week ago, it's reported in the discussion meeting. It's gone. Keep watching. What on earth might be happening? So this, as it were, model may give you an idea. This is actually mostly a picture taken with Hubble Space Telescope of CW Leo, which is also a carbon star, much nearer than TU Taurus. What this picture shows us is the dusty shells that have been blown off periodically by pulses from the carbon star. The carbon star is actually right in the middle and has or a diameter, maybe that an astronomical unit, which is the distance sun to the Earth, or maybe more. So it's, as it were, in this kind of picture of things, relatively compact. But these shells, these dusty shells, will go out to something, tens, 20, 30 light years, in the final stages. So a huge expansion. And notice, of course, they're not even, they're shells. This A-star companion has been drawn into the picture of Hubble. Apologies if needed, but just shows us that what we think is this A-star companion is moving around its primary, the asymptotic carbon star, big giant star, and it passes through these various shells, which will block the light, let it go through, block it again, let it go through. And this, we know, has been happening for years, thanks to actually the database at Harvard Observatory, Cambridge, US, which has photographic plates going back, decades, even 100 years ago. This phenomena has been happening of the A-star companion appearing, disappearing, but without any real fixed period. So mysteries continue, and we need to keep observing it, but this looks like the scenario. In a few million years, the TU Taurus system will be completely different. The carbon star will have thrown off its outer shell, creating a short-lived planetary nebula, transforming the core of the star into a white dwarf. The A-star companion will evolve to become a G or K-type red giant. So that's the one we saw. So that's going to evolve, going redder, showing unusually high abundances of the S-process elements. Thus, TU Taur will transform itself into what astronomers call a barium giant. We've caught it in the act of forming. TU Taur is a glimpse of the stage of this process that we've never seen before. I hope you're saying, wow. So the fun of, as you know, of telescopes observing, and certainly of spectroscopy. I said that a telescope that you don't work on dies. It's a living thing. VATT has now become robotic. Thanks to the work of Project Soft. Now, we've been exploring since certainly a good 11 years. Project Soft started 2022 with a contract signed, financing secured. But we've been looking the previous 9-10 years for how to get that robotic. My design team right at the beginning, 35 years ago, designing that and more, always thought of it as eventually being robotic, but then the equipment to do so wasn't readily available, and it's quite a project, as well as the funds. Don, because a generous donor in memory of her husband, Donald, who is an enthusiast in astronomy, gave us a lot of the funds needed to do this conversion. We went with Project Soft because, as you can see from this illustration of telescopes, they had done 2-meter class telescopes successfully beforehand. Just in the spring this year, we had the commissioning of Don. So a great step forward. Yeah, that is a problem. And this gives you an idea of the, kind of its optical scheme. We've seen the mirror there. We've got the secondary mirror there, which I always think looks a little like a cardinal's hat, sending the beam down to about an F9 at the focal surface there, which of course is curved. We don't have focal planes, we have focal surfaces. And the whole problem is to keep these two both in pistons, so the distance between them within 2 microns, as well as the tilt and the displacement in X and Y of the secondary mirror with the same kind of accuracy. That's a problem to do it and keep it there. The hexapod is helping, but how to make all this automatic and work into the future? And that's not the only thing. This obviously is an equatorial mount telescope, and that is out azimuth. But it gives you the idea there are systems all over. It floats on oil. So there's oil tank, temperature of pumps, pressure of nitrogen, pressure of oil, all kinds of systems you have to keep monitoring to make sure they're safe and performing correctly. It's a huge project to automate or robotize a telescope like that. But it began, so this is the installation of Dawn happening. What we see there is I think it was April the 2nd this year, taking the box with the various electronic equipment which had arrived from Prague, from the Czech Republic, from the large binocular telescope, which is off to the left, through the intersection there and up to VATT, which is on the right. And of course, we picked a nice snowy day to do it all. So that's fun, but okay, it can snow late in the season. Just to illustrate, on the left-hand side, left-hand part of this is the old telescope control unit with computers and equipment which were the height of technology in the 1980s. That's why it needed replacement. It's amazing it had done so well for so long. All this we see on the right, including the amplifiers down here, is replaced. Well, the control equipment there and the amplifiers further down. So the amplifiers. So it's amazing what this period of time, 30, 40 years, can do in miniaturization. Up in the dome, we can maybe see this is the side of one of the forks of the telescope and a whole bunch of electronics there, wires to bring it up. This is the dome and control for the dome, etc. All kinds of things to keep it in order. But when all that's in place, then you also got to tweak it and make sure it works with the software. So basically the software too. The two from Czechoslovakia here on the right, our own CJ, electronics and computer engineer at the University of Arizona. And this is Paul Gabor, our vice director. And a couple of 4K screens there, which you use when you're observing, one with all the controls for Dawn, and then to see what you're looking at kind of with the telescope. So there we go. The joy of it, of course, this is a kind of an operations screen. There are many other screens you can click get hold of by clicking down here, different panels. This one has the joy of start of telescope on. Before Dawn, before making it automatic, to start the telescope, you'd go up to the dome, which is kind of the floor 3.5 of mezzanine, and go up to the telescope. You do things there, you do things down on the 3rd floor under the telescope. You'd go down to the basement, then you'd come back up to the 2nd floor where the control room is, where you saw that equipment for the telescope control system there. And then you'd go into the dome and switch on the cooling system for the making the mirror, conditioning the mirror to the same temperature as the outside air. And you'll come back. It would take, if you're really quick, it would take half an hour. Probably more like 3/4 of an hour, and if something went wrong, it would obviously take a lot longer. Now you push start on there, get your cup of coffee, and 3 minutes later it says, ready, where do you want to go? So remarkable. We're happy. How can you operate it? The legacy mode, which is basically as we're doing now, but the start up and shut down are fully automatic and take a very short time and no running up and down. You just sit at that 4K screen. Scripts for collimation and focusing, okay. Become there. Remote mode, so we can operate it from, oh, how about Castel Gandolfo? Remember seeing that picture? It'd be daytime there when you're operating that. Maybe that's what to do. Scripted mode, where you give it a script in the afternoon and then go to bed and see in the morning what's happened. It's quite transformed. Why do you want to do the? Oh, we'll come to that in a moment. The result of doing Don is that its pointing precision is now 3 arcseconds root mean square. It used to be huge. I'd go to another part, slew to another part of the sky. I'd have to find a bright star to zero the coordinates on, and then go to the star, the science star is interested in. It now goes 3 arcseconds. And in these first months, users are using the VATT in the legacy mode while developing scripts for their own science cases. So we're very much, startup now. After the summer, 2 months of rains in Tucson, July and August, at the end of this week, we're going to get observers going up to check out and see how things are going. Tweaks, yes, there's always going to be tweaks, target acquisition, guide star acquisition, collimation. The hope is that to do that automatically, and maybe that should last about 10 nights. Yeah, that'd be nice. Rather than having to do it at the beginning, collimation at the beginning of every night, and then doing focus, and maybe tweaking the focus through the night, which doesn't quite follow, the algorithm doesn't quite follow the temperature and the flexure of the mount through the night. So, wow, this will be great. More science. So what is Don letting, us observers at VATT do? Preventing failure. So it keeps a real eye on when systems, are in the right mode, the right bracket of whatever it might be, temperature in the right range. And then letting that attract exciting science, time domain astronomy, things that go bump in the night, maybe like TU Tau, and other things that go bump in the night. Time domain is a very important kind of astronomy for this 2-meter class type of telescope. Rapid follow-up to survey discoveries. We're getting the Vera Rubin telescope, or the Large Synoptic Survey Telescope, its engineering name, coming along. Wow, that is ready for the new phase in astronomy. Okay. This is M3 by Don, unguided. I think it was 3 or 4 minutes worth, maybe shorter. Its pointing is so good. For short periods, we think up to about 10, maybe 20 minutes, it will not need guiding or automatic guiding. We're excited. Hope you are too.
All right, thank you.
Okay, I can now get out of this.
Does anybody have questions?
Oh.
Like to find anything out further? I was kind of wondering why the Gregorian design was used over something that we're more familiar with, like a Schmidt-Cassegrain or a RCT.
Oh, you mean the optics of that?
Yes.
Ah, yeah. So I'm trying to stop sharing. Where, maybe if I just, I'll get out of this.
I thought I'd read that the Gregorian was really, really good design for minimizing coma, but seeing that you have a curved surface area for taking the images, I'm not really sure that I read that correctly.
Okay, I'm now back with you. So yeah, being, of course, the heritage of Pope Gregory the 13th, we thought we'd take the Gregorian chance. Sorry for the that was a long time ago. With it, so because it's such a fast primary, you don't lose, your telescope doesn't get larger by going with the Gregorian configuration. So the Gregorian is having the secondary mirror in front of the focus, and you gain a slightly larger, the field of view is kind of a bit flatter, over a larger distance. So that there are gains in that, and certainly a gain was not lengthening the telescope. So Ritchie-Chrétien, Cassegrain, you have the secondary on the other side of the focus from the primary mirror. So this is making everything squat. So that fits inside of a 7-meter dome. So it's tiny, again, minimizing, dome seeing. So these various things went into a consideration. Does that sound okay to you?
Yes. Good enough.
You can do it with an F1.
Yes.
Simply. And so because we could do it, we did it. The other decision which remained, to be down the line was whether it was going to be equatorial mounted or Altaz. And when people asked, we said, yes, it's going to be one or the other. And then, the things for having it Altaz built up. It needs a derotator, so because the field of view with an Altaz rotates, as you know. But this was worth doing in order, again, to have a more compact telescope and one with less metal around it, producing heat. So the whole thing was trying to get the best possible return for the excellent seeing up on Mount Graham.
Do you have any active optics?
You hear the question. Do you have, Chris, do you have any active optics? Adaptive optics, sorry.
Oh, adaptive optics.
Yes.
Yeah, we kind of thought of it. The problem is getting, our secondary mirror is about 15 inches diameter. The problem is getting an adaptive secondary. Okay, you might do it at another place, but then you lose light, kind of almost as a tertiary. So we're thinking of that. In the infrared, simply tilt, being able to joggle it would produce a wonderful, return in image sharpness. We haven't yet done it because actually we don't yet have regular infrared instrumentation on it. We've had both a camera and a spectrograph infrared in the past, but those performed so well at VATT that they went elsewhere. So yeah, these are possibilities. At the moment, if we really want, sharp imaging, we knock on the door of our neighbor up at the top of the mountain, which has the large binocular telescope, which has something like a 22-meter, from one end of one of the mirrors to the end of the other mirror. So we've got a huge baseline for the large binocular telescope when it's used in interferometry mode. And so maybe we need to take a look at TU Tau and see if we can find a companion. That's when it becomes visible again. Then we need to get a kind of target of opportunity and let the large binocular telescope jump on it.
Thanks, Chris. Great presentation. Just a question with what you witnessed for the last 30-some years operating the scope. Any humorous or scary or funny stories of, something happening in the middle of the night, or, fires in the area, or something going wrong mechanically with the scope that caused a lot of alarm? I just wondered if there were anything that comes to mind through the years, because you must have had some incidents there.
Nothing occurs totally shocking, to be afraid. So it's disappointing. Nobody's tried to fire bullets at it. But at the beginning, there was vast opposition to using Mount Graham, for astronomy. Now, Mount Graham is a huge mountain. If you get a piece of, squared, mathematics papers, the little squares on it, and that represents the, acreage of the mountain. If you take one of the squares, that's what the observatory is occupying. So in terms of the, the use of the mountain is very small, but other people had other ideas, and the press got hold of the wrong end of the stick, as they generally do, and certainly not the facts. So there was quite an opposition. So yeah, we've had fun with basically Earth First terrorists at one stage, but no, because it was the only telescope I know with a police force permanently based at it. It hasn't actually resulted to anything. But, the police dogs were fine and everything else was kept well. So that's kind of the environment. But otherwise, it's anything seriously. It's just a tricky telescope, F1, up there and distance away. Things are, yes, they go wrong. You need replacing. So people are saying, oh, it's now robotic, it'll all work wonderfully. I think, yeah, if it works 5 years wonderfully, I think we've got done well. We'll have to do repairs and things and tweak things. So it's always the thing with the telescope. So a lot of fun. The projects done with it, basically, monitoring kind of projects, or the kind of the search, the exploration, the search kind of things. So, which a telescope like this, that you've got lots of time on, can do. With Richard Gray, a lot of time spent on looking for true lambda Bootes stars, they call, again, A-type stars that have a very peculiar atmosphere, and looking for candidates for that to see if they help pin down the distribution of them and try and understand the phenomena. It was pointed out in an atlas in 1943. So that's over 80 years ago. But the problem is still there, quite what the mechanism causing the strange atmospheres of these stars is. So that's been, it's wonderful for that kind of project. Yeah, or like the Eden, which I said there, for the looking for the transits of various planets across their stars. Yeah, so initial days of fun with Earth First, and likewise people settling down, though one always needs to be vigilant. The recent, just last weekend, an incident of people up at a university facility on Mount Lemmon, which is just north of Tucson. 3 people got into the compound, and they shouldn't have been there. But there we go. That happens. Otherwise, Mount Graham is a wonderful place. I can really understand why, people who enjoy mountains, were opposed to having any disturbance there. It's a beautiful spot with all kinds of animal life there. I remember a bobcat. We've got a 2-mile access road up from the main, what I call the Trans-Graham Highway that goes along the length of the mountain. I remember a bobcat following me down at the top of our 2-mile access road. There's all kinds of life there. Not the last time, I think the time before I was up there, and there were deer there. They hadn't noticed I was there. I was about 20 feet away, and it jumped up from the side of the road. That's amazing. It's an amazing spot. I can understand the opposition. On the other hand, telescopes are about the most benign thing I can think of for Mount Graham. When at the beginning of the 80s, when I first came here, actually strictly 84, there was a survey being done by the Forest Service to say, would you do you think that a ski resort up on Mount Graham would be suitable? Now, this was the picnic day for people from Stewart Observatory, and I think most of them answered not at all. But those are the kind of things that do change a mountain. But astronomy, no. I think we know it's quite benign, and if anything, it preserves beautiful mountain. Even with, well, the annual, accumulated snowfall is about 10, 11 feet worth. There's a good amount of snow.
I had a question for you. How do you ever correct for coma with that fast a telescope?
Well, again, by the you do it with the secondary and the adjustments of that. There are 6, ways of adjustment: up, down, side to side, and tilt. Okay. And that's what you connect. The thing has been that the secondary mirror itself is highly. I hope I'm looking for the right word. It's not a standard parameter. It's amazingly.
It's not flat. Secondary.
It was made by hand, and by a firm up near Boston, and 2 people had a go with it, and eventually they got it right. Spent a lot more money, time on it than the money in the contract, but they achieved it. Remarkable thing. So I think it's that design. The field doesn't go out that far at the moment. It's limited by the hole in the primary, which was exactly scaled down from what would be the large binocular telescope size, so the 8.4 meter sized. And so the result is that we only get a field of 12 arc minutes, through that hole. So that also helps the image quality. If you went further, yes, you would have problems.
Okay, I have a question, second question.
Yeah.
So it looks really dangerous to lift that mirror up to go get it recoded.
Oh, yes.
So why is it that there isn't a coating facility on the floor next to the mount?
Because it's big and it's costly.
Well, I don't imagine it's cheap getting a crane up there and taking it down and the potential risk of dropping it.
It's a lot less than taking it down to the university's, reluminizing facility near the university. So far, what we have obviously looked at but haven't yet solved is, could we bring that mirror down inside? You saw the outer silo. Could we bring it down inside that? We have not yet, found a good way of doing that. Still working on it. That's one of Michael France's. You saw the picture of that engineer, one of his pet things. Yeah, we're getting close. Maybe one day we'll do that.
Well, I think that wraps it up at this end as far as questions and all go. So again, Chris, thank you very much for a very enjoyable and informative presentation on the Vatican telescope. Thank you very much.
Well, thanks so much for your attention too. Indeed, been a pleasure to be with you, and may your club thrive in all kinds of ways.